Right. Well, before this evening's talk, let me duly welcome, welcome back, Danielle. You've spoken to us before, some years ago now, but we'd like to welcome back Professor Danielle Schreve and onto this Zoom edition to Essex Rock and Mineral Society. Professor Schreve is head of the Department of Geography and Professor of Quaternary Science at Royal Holloway, University of London. Danielle is involved in a tremendous amount of research, notably in climates and environments of the last 2.6 million years, otherwise known as the Ice Age. Danielle's main area of research is in the traces of Iron Age fossil mammals, looking at how these animals have responded to both long-term and abrupt climate change. Now, I need to say right now that I have a particular personal interest in this research, as I am myself an Ice Age mammal, and I want to know how best to respond to abrupt climate change. So I hand over to you, Danielle, with all due concern for your talk, Move, Adapt, or Die.
So thank you very much for having me. Yes, Ian, you already know the answer to the secret of surviving the end of the last ice age, which is move, adapt, or die. And I think probably that's wise words for all of us. So I am going to be talking about the Quaternary, and although broadly speaking, people refer to this as the Ice Ages, of course, I often, when I talk to groups far less informed than yourselves about the Quaternary, people are often looking a bit blank. And I say, if there's one thing that I want to get across to people, it is that actually the Quaternary is important because it's the period that we are in today. So it's really obviously significant in terms of thinking about not only long-term change, the glacial to interglacial cycles, particularly that have happened over the last million years, but also the very abrupt changes that we have at the very end of the last ice age. Can I just check, because I can see the bar with all the little buttons and things at the top. Is that on the screen where you can see it, or is it not?
No,
fine, then that's perfect. Good. Okay, no, it's just yeah, I'm slightly hesitant to start moving it around. I'm going to drag it to the bottom. Right, hopefully that won't distract anybody. Fantastic. So that's our long-term perspective. But in fact, if we then, sorry, for some reason this is not wanting to move forward tonight. I don't know what's going on with this. It's locking up, which is most frustrating. There we go. Clearly, I just need to press very, very hard on the laptop for some reason. So when we look at, in particular, the record of the last 100,000 years, so you can see this is actually a graph that is taken from the Greenland ice cores, so drilling down into the ice cap in Greenland, and it produces what is effectively an annual record coming from about 125,000 years ago, where we have the last interglacial coming down through incredibly rapid, abrupt climate changes, particularly over that period between about 60 and 30,000 years ago, which you can see on the bottom running across from right to left. And then as we come out of the last glacial maximum about 20,000 years ago, we rise up sharp, rapid climatic warming into a period that we refer to as the late glacial. It all goes wrong again. We descend into savage cold at about 12,000 years ago. And then, of course, we warm up into the Holocene, the current interglacial, at about 11,500 years before the present day. And the Holocene has been pretty stable ever since. There's been a few sort of climatic blips. You can see one at about 8.2 thousand years before present, but otherwise it has been a period of relative climate stability. So one of the things that interests me is this big question about whether species move, adapt, or die out in this particular period. You can imagine that over the course of the last 100,000 years, there has been a tremendous amount of ecological stress, particularly on a lot of the megafauna. So the largest animals, the ones that are slow to mature, they have few offspring. If anything, perturbs their range, their behavior, they take a long time to recover their numbers. So this is one of the reasons why this is a fascinating period to study, because it's a period when there's a lot of ecological change, there's a lot of climate turnover. It's also the period, of course, when Neanderthals are going extinct from about 60,000 years onwards. And from about 40,000 years, we see our own species, Homo sapiens, coming into Europe. So understanding about the fauna provides a fascinating backdrop, really, to human evolution and behavior. And one of the things that I had been curious to know about was whether what we see in the literature often described as disharmonious faunas, particularly for that period of the late glacial, right towards the end of the last ice age. We are in a situation where obviously climate is changing rapidly, species range are changing rapidly. And we frequently find accumulations of species that today do not co-occur. And in the past, those have been described as disharmonious faunas. I always find that a bit weird because it's a strange expression. It really judges everything by the present day. So just because it doesn't look the same as the present day, we call it disharmonious. And there's been a big question about whether these faunal assemblages were real, or whether it was just an artifact of the fact that we didn't have well stratified sites, well dated assemblages, and actually there had been some kind of taphonomic mixing. So that's been a big question for me in terms of investigating the faunas of this period. So I love this quote. This is a quote by the journalist George Monbiot from his book Feral. Paleoecology feels like a portal through which you may pass into an enchanted kingdom. So this is great because, this describes in a very nice way what I spend a lot of time doing when I get away from being head of department. And actually, it's this process of understanding the past, and in particular, as we'll see at the end of the talk, what that knowledge can bring to us at the present day in terms of making better informed conservation decisions. So obviously, as the name implies, paleoecology is the ecology of the past. When we think about modern day ecology, ecologists have a big advantage in that they can go out and they can observe species today. We obviously can't do that, but we have the advantage of time on our side. Ecologists deal with records that may be decades long. They may be, you might get 150 years worth of record if you're really lucky. Whereas, of course, we have at our fingertips, we have records that date back thousands, tens of thousands, even hundreds of thousands of years. So what that gives us is a much deeper time perspective and the ability to get a more accurate picture of the totality of species range in the past, the types of prey that they might have hunted if they were carnivores, the kinds of competitors that they may have had, the types of climates and environments that they may have endured. When we think about where species are distributed today, in many cases, particularly for species that have been persecuted or affected by habitat loss, by human activity, we can often see that they are constrained in very limited areas across the world. And it's wrong, in fact, to think that they have retreated to areas that may be particularly suitable for them. In fact, they may just be constrained to areas where they have been able to survive. And, without the knowledge of where those species have been distributed in the past, that would give us a false perspective on how and where we might conserve them in future. So having this deeper time record is really important. So into the Enchanted Kingdom we will go. So just a few words about the caves in the Mendips. So having really spent the early half of my career working in the Thames Valley, working in East Anglia, I'm now very much rooted in another sort of calcareous landscape, but this time with limestone caves, and especially down in the southwest, although I'm also working in the Peak District and in South Wales. The Mendips have fantastic records in terms of fossil material. So obviously caves act as incredible repositories for material coming in, and that material can come in through various sources. It can, for example, be the remnants of species that are living in the cave. It can be the prey of those species that might be living in the cave, and that might be small mammals that are brought in by birds of prey. It might be larger herbivores come in as the result of carnivore activity. There can be animals that fall through natural pitfall traps into caves, material that's washed in by underground streams. And obviously, of course, humans will play their part in caves as well. So caves can be complex places to investigate, and obviously, just as the same as we would do with any other site, a detailed understanding of the sedimentary infill of the cave is absolutely essential. In the Mendips, we've got the advantage of a really long chronological span as well. So obviously it's not continuous, but we know that the sites there range back to 1.2 million years ago. And just as an aside, I've put in an image at the bottom right of the quarry at Westbury Sub-Mendip. So this is no longer an active limestone quarry, but when it was being quarried in the late 1960s, a bit of over-enthusiastic blasting took down the whole of the northeastern side of the quarry, and the face dropped away and exposed this astonishing cross-section through a huge cave system. And this site was the subject of extensive excavations by a team from the Natural History Museum in the late 70s through to the 1980s. And just an astonishing array of vertebrate material recovered, most of which is about 500,000 years old. Most recently, we've been working at this site on much older deposits, the oldest part of the infill of the cave system there, which is 1 to 1.2 million years old. And we've just published the remains of the oldest hippo in Britain, which you can see top right. So this is another story, but maybe for another time. But a fantastic chronological span, which obviously allows us to examine the record from different time periods, cold stages, warm stages, and so on. So these caves also preserve, in many cases, rather continuous records for the period of time that is represented there. So there's lots of different analytical methods that we can throw at them. Especially for the younger material, we're able to use, for example, things like geochemistry, so stable isotope analysis, ancient DNA, and obviously for anything under 50,000 years old, we have the advantage of radiocarbon dating at our disposal. So there is great potential for high resolution paleoclimatic and paleo-environmental change in terms of our understanding. These caves also preserve the record of early human activity. It becomes more abundant as you get through towards the present day, but certainly at Westbury 500,000 years ago, there is indication of humanly worked or cut marked bones. And then from later periods, we've got things like the celebrated Upper Paleolithic material that has been cannibalized from sites such as Goff's Cave in Cheddar Gorge. And furthermore, a long history of investigations. So actually the antiquarians themselves are also very interesting in their own rights. And there's been a huge amount of work done over decades now that have been reporting on this material. So I've just shown some of the beautiful illustrations from the Paleontographical Society monographs, which were created largely from the sort of mid-1800s to about 1920, 1925. And you can see those beautiful lithographs. We've got some from the wolves shown in the center. We've got the bears over on the right, and the monograph on the felids with some splendid lion jaws shown in the bottom center. And many of these remains were collected by obviously antiquarians of varying sorts. But one of the ones that I want to draw your attention to is the chap on the left. So this is William Beard. He was a local farmer from Winthill in North Somerset, and he lived at the aptly named Bone Cottage. He was obviously not a man of formal learning, but he was incredibly diligent and very assiduous in documenting where material had come from. This is in contrast to other collectors at the time, particularly a reverend gentleman who wrote his own name on the bone but didn't bother to tell anybody where it had come from, which has been a bit of a puzzle to put some of these sites back together. But you can see Beard sitting there at Bone Cottage. He's actually holding in his hand an early last cold stage or early Devensian articulated bare paw from the site of Banwell Bone Cave, and near his right elbow he's got a fabulous skull of a cave lion from the site of Sandford Hill at about 40,000 years old. So yeah, so very lucky to have had this diligent collection in operation. Bottom right is a figure known to many people. This is William Boyd Dawkins, of course, you know, a learned scholar at the time, pioneering work done at the Wookey Hole Hyena Den and many other caves around there. I like that photo because he looks like an archetypal Victorian villain there. So some very different characters involved in collecting this material. So I'm going to take you away just to the south of Bristol. This is a National Nature Reserve at Ebor Gorge. If you know Cheddar Gorge, it's just up the road, but here we are just a few miles outside the village of Wookey Hole and a few miles to the north of the cathedral city of Wells. So this is a limestone gorge. It's cut in Carboniferous Clifton Down limestone. It was probably cut about 1 million years ago, estimated by the British Geological Survey. So this is a period when small local rivers began to cut down across the Mendips Plateau, and it's believed that the gorge was excavated then. So it's a very different prospect to Cheddar Gorge. If you know Cheddar, you'll know that it's awash with gift shops and tea rooms, whereas this is just an undisturbed National Nature Reserve. And you can see in the bottom left our little cave site that is up on the flank of the hill. It's called Gully Cave. I didn't name it, but it's named because of the gully, which you can see leading up towards the plateau at the top. The floor of the cave is, the floor of the gorge rather, is quite well known for a series of small caves, many of which were excavated in the early 1900s by the founder of the Wells and Mendips Museum, Herbert Balch. And those are small caves, and they contain generally sort of later prehistoric, so sort of Bronze Age or Neolithic material, going up to a bit of Romano-British material. There hasn't been any Ice Age material found anywhere else in the gorge, apart from a small cave site called Bridgepot, which was excavated by Charles McBurney of Cambridge University in the 1950s. So I will show you what the site looked like when I was first taken there, which was in 2005. And you can see on the left-hand side, you can see the light at the top. This is the gully. It's now rather overgrown, actually. And the entrance was about 1 metre wide and not even 1 metre high. And we had to pick our way very carefully along the side of the gorge. It was pretty steep. And when we got to the entrance of the cave, I was able to crawl in on my belly. The cave was pretty much full of sediment. There was a limestone ceiling right above me, a bit of discarded badger bedding, and I really couldn't see anything else. So we were fortunate in getting permission from the National Trust and Natural England. So the site is actually owned by the Trust, but it's managed as the NNR by Natural England. And they gave me permission to put in a trial trench the following year in 2006. So our first trial trench was a big success because we got into a red limestone breccia. Just broken up clasts of limestone, variably supported with matrix, which turn out to be mostly silts, some clays in places. And in fact, actually, in this picture, it's just that top right-hand area that is our original entrance. The National Trust originally asked me to leave half of the cave undug as a repository for the future. So this was a bit of a challenge, because how do you say what 50% of a thing of unknown dimension is? So completely arbitrarily, I said I will dig on the north side of the cave and we will leave the south side as an archive of sediment for the future. And the aspiration, the reason for doing this, was obviously because caves have been completely emptied out in the past, and it would be a very good thing to have the opportunity to go back in future and to examine the deposits. So this was what we tried to do. Ultimately, it was to prove unsuccessful, and I will explain why as we go along. But this is the situation from about 3 years later, in about 2009. Our very first trench that we put into the red limestone breccia, I took some samples, I brought them back to Royal Holloway. We wet sieved them through a 0.5 millimeter mesh, which is our standard process. And within those samples, I found the remains of a tundra vole species that obviously is absent from Britain today and had not been here since the end of the last ice age. So incredibly exciting. We knew that we were onto something, and it was worth proceeding. So as we went, we began to explore towards the back of the cave, trying to leave this bench of sediment on the right, but the north side of the cave started to expand further and further. And we began to trace the outside edges of the entrance, where you can see the limestone coming down here and here. So our works continued. There you can see the situation several years later. So our former entrance is right up at the top right-hand side of the hole. We've now got quite a deep hole. It doesn't go very far back. So the cave is about 6 meters deep. And at this, so 6 meters deep front to back, and at its maximum, we're at about 6 to 7 meters down inside the cave. Now you can see there, we are still trying to preserve this witness section, this archive for the future. We have now had to resort to a system of scaffolding and boards to try and keep the thing intact. And that was the way that we were proceeding. So it obviously cut down the area that we had to explore over on the north side. So this is the deposits inside. You can see it's this classic sort of cave earth. It's a red limestone breccia, and the deposits themselves record the legacy of past climate change. So at points where we have had very severe climate conditions, it's a much coarser deposit. We've got large blocks of limestone and they are unconsolidated. There's very little sedimentary matrix that's binding them together. At other times, we have got much more silt or clay holding the matrix together. So again, recording a time when there is more vegetation on the landscape, there's less material actually coming into the cave, presumably largely down the gully at this point. So coming down the gully from the plateau and dropping into the cave. There are some sort of pipes in the now blocked in the roof of the cave, and potentially sediment could also have come down through that way as well. Now you'll see that it's very red. It's actually quite easy to trowel in the middle of the cave, but towards the margins of the cave, where we have the sediment butting up against the limestone wall, you can see that it's very white. This is actually concreted, it's cemented in situ, of course, by carbonate-rich waters from the dissolution of the limestone, percolating down under the drip lines, down the side walls of the cave, and just cementing that breccia in situ. So where we do find bones in that breccia, they are a trial to get out because they need drilling and chipping to get out. Anything else can be relatively easily troweled away. And capping the sequence, you can see the close-up here, this bright white flowstone. You can actually see it following the way all the way along the back of the cave towards that light at the back. So eventually the cave was infilled and it was capped off with a flowstone floor. It's discontinuous, but largely intact, apart from a place where a badger had gone in at the back. So that's basically been very fortunate for us because it has sealed the cave deposits off, and nothing has disturbed them until such time as we were able to go and explore them. So in total, we have excavated over 300 tons of sediment from this cave. We have done it by hand. We dug every year apart from 2008 when I just had a baby, and obviously 2020 when we were not allowed to go because of COVID. But we have been there for 2 weeks with a very small team ever since. We excavate sufficient that it keeps us busy for over the following year in terms of processing it. And we have massively oversampled this cave, but because of its importance, it has definitely merited that. So we've actually sampled over 65 tons of sediment from inside the cave. There's also more from outside the cave as well. And all of that material has been boxed up and taken back to Royal Holloway, where it is sieved through a 0.5 millimeter mesh. It's dried, and then the residue, very painstaking, very slowly, is picked out under the microscope, all of the small fragments, the teeth, the bones, any shells. So we're looking at all our small vertebrates, mammals, birds, reptiles, amphibians, and fish. So extensive amounts of processing. We also record with a total station in 3 dimensions over 4,000 large mammal and bird remains. And we record anything that's larger than about 2 centimeters in diameter. So we've got a fabulous array of larger material as well. And by the time we have finished, I'm confident that there will be over 1 million microfaunal or micromammalian remains, bones and teeth. It is so spectacularly rich. In fact, it is, it's actually quite a challenge for me to be working on this material because there is just so much of it, but it's an astonishing repository of material. So I'm going to see if this works, but this is going to be, this is done by a laser scan. Periodically, we get the cave scanned. And what this is doing is allowing us to have a 3-dimensional record of the inside of the cave, so that when the deposits have gone, then obviously we will have our 3D record of the shell of the cave and our 3-dimensional record of all our finds, so they can be plotted as a cluster, a cloud of data within the shell of the cave. So we'll just see if this works, and the observant among you will notice that we are going in through a new entrance, not the one that I've shown you, but a new lower entrance, and I'll explain a bit more about how we found that a little later on. So we're coming from the outside of the cave. The upper entrance is covered in a blue tarp, which is what's giving it that slightly spooky look. And we now know from clearing the sides of the cave that it sits in a sort of semicircular depression. We've got a gate on this lower entrance now, and we're just coming up into the inside of the cave. So roughly 6 meters to the back, you can see there's like a sort of quite a pronounced alcove at the back. And then spinning around, obviously the highest and youngest deposits, which are now removed. So these go all the way up to the early part of the Holocene. So you can see we've just got the exposed limestone here. This is after we have had to remove the archive section. So it's a relatively confined area to work in, but that hopefully gives you a bit more of a sense of what it's like to actually be inside there. So the upper part of the cave, we have an age model for it based on radiocarbon dates. And you can see there, we are looking at the period that covers from about 20,000 years ago, coming through time. So this time the climate wiggle, also from Greenland, is reversed. So the oldest are on the left-hand side of the slide, and coming through time. So this period on the left-hand side is the period of the last glacial maximum. So very cold periglacial environment in this part of Somerset. Obviously, ice sheets expanding further into Wales and across into the northern part of East Anglia. Then we have rapid warming at about 14,500 years before present. This is the late glacial interstadial. Some climatic oscillations in that period. We descend into a period of cold climate, the Younger Dryas, and then we warm up at about 11,500 years before present into the Holocene. So the upper part of the cave covers this time zone, excuse me, covers this time zone. And we can see that, in fact, our mammals, so these are radiocarbon dated remains of mammals and also some birds as well. And they cover the period from the late glacial interstadial, where we have got things like Arvicola, the water vole, early on in the interstadial at about 14,500 years ago, but also things like deer, wild horse. As we come into the middle part of the interstadial, this part of southern Britain is becoming more wooded. There's a spread of birch woodland, and horses seem to disappear locally because they're open ground indicators. And instead we have red deer present in exclusivity. We then come into this period of climatic decline, the Younger Dryas. We've got things like Arctic fox that are present, ptarmigan as well, wild horse and reindeer, and then the rapid warming up into the Holocene. We have things like reindeer that are clinging on into the early part of the Holocene, but eventually it becomes too warm and too wooded for them. Instead, we have other things like Bos primigenius, the aurochs, coming in bang on the start of the Holocene. And then by about 10,000 years before the present day, we have got the cave pretty much infilled. Our youngest specimens are things like mountain hare, which of course don't live in southern England today, and also wildcat, which you can see here. So that's the upper part of the sequence. So covering essentially 14,500 years, this sort of almost like a false start to the current interglacial, a period of climatic oscillation, decline, and then the warm up into the Holocene. And by the early part of the Holocene, the cave is infilled, it's capped off, and there's no possibility for any more occupation. So what I've done here is just to show you those different phases, the late glacial interstadial, the Younger Dryas, and the early Holocene. And you can see the radiocarbon dates, so years before present. These are calibrated years before present, shown on the left-hand side. And I've color-coded the species, red for species that occur in southern England today. We've got green for species that occur in Britain today, but which are not present in the southwest, and blue for species that are cold adapted and which are exotic to Britain today. So you can see that within the interstadial deposits, we have got a real mix of species. So we've got everything from things like short-tailed field vole, common shrew, pygmy shrew, water vole, things that are living in southern England today. They require quite a lot of shrubby ground cover, for example, but equally mixed in there a number of exclusive cold adapted taxa. So things like collared lemming, which today has a circumpolar distribution. Interestingly, the Norway lemming, which is also another common cold adapted species, is absent at this time. And we have a new record of wood lemming, which is also found in Scandinavia. So those cold species, some also tundra voles as well, the narrow-skulled vole, but also northern vole present. We have things like wild horse, as we know, present early on, but the red deer continue throughout, even though the wild horse disappear. So in total, a mix of habitats at this time. There's clearly tundra vegetation around, so cold climate, even though we've still got, we're in a briefly warmer period of that part of the last ice age, but it's still cold. There's still tundra habitats, there's still plenty of representation by cold adapted taxa, but also some wooded or shrubby habitats also represented. This is genuinely a disharmonious community. So our sampling, we're sampling every 10 centimeters within specifically delimited squares within the cave, and it's very clear that these are this is material from for example, individual owl pellets that have, from birds that have been hunting over the landscape. They've come back, roosted in the cave. That's how the small mammals get in there. And they are incredibly rich. And there is this genuine coexistence of species. There is no evidence of adaptation at this time, simply because there is insufficient time for, for species to be able to adapt. It's so rapid, the degree of climate change. Oops. So moving on into the Younger Dryas, period of climatic deterioration. And you can see that the blue is the dominant picture here. So we're at about 12,500 years to about 11,200 years before present. So Norway lemming, collared lemming, and very excitingly, a rare record of steppe lemming all the way from eastern Siberia. We do have things like mountain hare that are present, so obviously not present in southern England today, but present from the Midlands further to the north. So these are the varying hares that change their coats according to the season. But we also have steppe pika present. So these are a very sweet little leporids. So they're the rabbit and hare family. I'll show you an image of those in a moment. But those are characteristic of upland environments and come into Britain during this period of cold climate. But what's really interesting is there is still this persistence of temperate adapted taxa. You can see those shown in red. So we've got wood mouse, common shrew, pygmy shrew, water shrew, and some of the voles as well. And I think it's probably likely that in these areas of quite complex topography, these steep limestone gorges, we have obviously the plateau would be a pretty savage place to inhabit, but you would have had more sheltered, buffered deposits or rather habitats occurring at the bottom of these limestone gorges. So this could have offered a degree of protection and stability, a refugial area for many of these temperate adapted species. Wild horse and reindeer are important in the record here, equally disharmonious in many respects. And the cave is an Arctic fox den at this time. There's a beautiful skull that I've put on the slide from a complete individual that was found curled up at the back of the site. So lots and lots of crunched bone. There's material that's being brought in by these small predators, but equally the cave is still being used by birds of prey. And here we can see the fact that we have these species coming in that are largely, they are not sympatric today. They are not living in the same places globally today. So at the top, you can see the steppe pika, Ocotona pusilla. So these are sweet. They're like a small rabbit, and they have this habit of collecting vegetation, which they store in larders over the winter to keep them going within crevices in the rocks. So they are characteristic today of Eastern, well, sort of Central and Eastern Europe and upland habitats. Dicrostonyx torquatus, the collared lemming, has a circumpolar distribution up in the high latitudes in this part of the Old World. The Norway lemming, which is present in Britain at this time during the Younger Dryas, is obviously an inhabitant of Scandinavia. Below it, we have got the very rare record of the Siberian steppe lemming. So this is Ligurus ligurus, today going all the way from Central and Eastern Europe into the central parts of Asia. And as I've mentioned, Arctic fox are very widespread, so occurring not only in the Palearctic, the Old World, but also the Nearctic and Greenland as well. So these species are coming together. The Younger Dryas is this exceptional snap of cold period that lasts for only about 1,000 years, but even these smallest animals are on the move and coming into Britain in response to this climatic deterioration. And perhaps the most unusual of all the species that occur at this time, we don't have it at Gully Cave, but we have it just down the road at various sites in Cheddar Gorge, particularly from Gough's Cave, are the remains of the Saiga antelope. So Saiga today, you can see their modern distribution in the map on the left. They're extremely endangered. They occur only in isolated populations in Kazakhstan, in Mongolia. But in response to this one-off period of extreme cold and in fact aridity as well, they expand their range all the way to the west to get into Somerset. In fact, they expand out towards Alaska in the opposite direction as well. You can see illustrated some of the remains that have come, they've been radiocarbon dated to the same period from Gough's Cave. And below you get a sense of the Saiga antelope. They always have been an arid adapted species. They have this fantastic nozzle-like nose that helps to filter the dry, sandy air in their desert environments in which they inhabit. So an extraordinary response in terms of climate change. And then finally, we get into the Holocene. So we're right at the top of the sequence. We're just about to see the infilling of the cave. And as you would expect, there is a predominance of species that we would find in southern England today. But interestingly, we now see new species joining them that are either obligate thermophiles. They have to have warm conditions. So things like the common mole cannot survive in a periglacial environment because of the frozen ground, so they need warm soils, but also arboreal taxa as well, so things like the hazel dormouse. So today, again, another endangered species, but one that requires continuous tree cover for its survival. The cold adapted species are still clinging on, so they cling on for a little while, but then eventually, just like the reindeer, they will go extinct because it's just getting too warm and too wooded. We know that aurochs comes in, a typical animal of temperate woodlands, so very consistent with what we would expect. And it's interesting that, of course, the early Holocene is actually just as disharmonious in every respect compared to what we have seen previously with both the Younger Dryas and the late glacial interstadial. For those of you who are interested in birds, we have fabulous remains of birds, just beautifully preserved. Birds are often very rare in open Pleistocene sites, simply because they're so fragile, but caves are great places for finding them because they are relatively protected once they get buried. So just a selection of species that we have at the site, and of course they also vary according to whether we're in a period of cold or more temperate climate conditions. So we've got things like red grouse, we've got grey-legged partridge, black grouse. We have some of the predatory birds, so we have kestrels, but also young kestrels, so they seem to be nesting in the cave. We have long-eared owl as well. There may, of course, have been other birds of prey that will have been agents of accumulation for the small mammals, but which we're not able to discern because we don't have their remains. Lots of remains of jackdaws, and in fact, some of them are clearly females who died during the egg-laying period. And that's because we can see a particular type of bone, medullary bone, which is laid down by nesting females. So an incredible level of detail. Presumably these birds died in springtime. And a fairly recent piece to come up. I was just astonished by the size of it, and no wonder, because it's a piece of great bustard. So a species that has obviously been recently reintroduced to Salisbury Plain, but which is thought to have been a native species and hunted to extinction. In this upper part of the cave, we've got no really clear evidence of human activity. There are no artifacts, there are no flint tools there. What we do have are remains of articulated limbs of larger mammals. And at the top, you can hopefully pick out just above the trowel, there is part of the femur, well, in fact, it's a complete femur of an aurochs. We also have the rest of the hind leg to go with it. And although there's no cut marks on it, it's a very human thing to do, to remove a haunch of meat and to take it into a place of shelter such as this. It's not something that you would generally see a carnivore bothering to do. So there's perhaps some indirect evidence that humans might have been around. Also, because we do pick up remains of bones that seem to have been smashed open for bone marrow. You can see on the bone here, just below, that we've got a green bone fracture that was made when the bone was fresh. It seems to have been smashed and twisted to extract the bone marrow, which would be highly nutritious. But it's also oddly discolored. Most of our material from these upper layers is this kind of yellowish, creamy color, like we see with the aurochs femur. And here you can see this is flushed with gray to black. It's not manganese staining, and we can't pinpoint any other type of alteration other than potentially discoloration that's the result not of burning, but of being in proximity to a source of heat. We did some experimentation actually back at Royal Holloway. We built on top of some cave earth from the site. We built a small fire using wood that would have been around at the time during the late glacial. It got up really hot to about 900 degrees within only a few minutes. And below the fire, we buried bones with flesh, bones without flesh at different depths. And we were able to reproduce this kind of discoloration from material that was buried perhaps, 5 to 10 centimeters below the hearth. So it's not burnt, it's not calcined, it's not white and crumbly, but you can produce this kind of discoloration from proximity to a source of heat. And it may well be that these bones were lying around and that a fire had been lit locally, perhaps just outside the cave. In fact, actually, this bone has been gnawed by something, perhaps a wolf or an early dog, and potentially they were scavenging from these campfires, took those into the cave. So that's one possibility for explaining. We've never found remains of a hearth. We have found fragments of charcoal throughout in these zones, but they're very small and we cannot say for sure that there was a hearth. So if we have any evidence of humans at this time, it's very much indirect. As we went down through the sequence, the deposits began to get coarser and coarser, and it was obvious that we were heading into a period of major climatic deterioration. So obviously this has to be older than the late glacial interstadial, and of course that makes perfect sense because the immediate period before that is the last glacial maximum, 25,000 years ago. And you can see how coarse the deposits are getting. We dug through these for 2 years we found almost nothing except a couple of bird bones. Those bird bones belong to 2 very cold adapted species, the long-tailed duck and an Arctic skua, which you can see illustrated here. These are both species which today live up on high Arctic rocky foreshores, are generally cold climate indicators. So almost sterile apart from that, but yeah, it's a good thing we have a laugh while we're digging in the cave, because otherwise I think probably we would have given up. But we had some indication that maybe there was something else below, because actually at the top right you can see a chunk of reworked flowstone which was present in this very coarse material, and that suggested that there had been at least some evidence potentially of a warmer period which had allowed the precipitation of flowstone. So it gave us encouragement to carry on. The period of the last glacial maximum is very poorly known for its fauna in general in Britain. It's a time when there's some dated muskox remains from the English Midlands. There's a few bits of mammoth and reindeer, but actually nothing else. So the fact that we weren't finding anything was no great surprise. But the next season, we got back down into finer grained remains, and it was full of bears. It was a brown bear den. Some of these bears were clearly very elderly and had probably perished during hibernation. At the top right, you can see a canine tooth. In fact, just the white bit on the right is just the stub of the tooth. Most of this is the root. This was absolutely worn down, exposing the pulp cavity. So a very elderly animal, probably in quite a lot of discomfort, and one that had probably perished during hibernation. But there's also remains of the milk teeth of baby bears. So it's clearly a time, there are bear remains of different ages, and adult and sub-adult as well, but the babies, it's just the milk teeth that are present. So these were clearly being reared in the cave and presumably then made their way out to the outside. Interestingly, at this point, some of the bear bones showed signs of gnawing by spotted hyena. So in fact, you're looking down on the end that's been completely chewed away. This is just sediment inside the center of the bone that we can see here, which is a humerus of a bear. And on the right, where the white arrows are, you can see puncture marks from these powerful hyena canine teeth. I don't think the hyenas are hunting these animals, but I think they're coming across animals either in a state of torpor and killing them during hibernation, or perhaps coming across the carcasses of animals that perished over winter. And around this sort of this time within the cave, we began to find these enormous boulders of limestone. They had clearly come from the upper entrance and the collapse of that upper entrance. They took a lot of drilling to get out, to smash up and to take away. But underneath there was an absolute profusion of bones. So, for example, remains of wild horse, remains of a huge red deer, and lots of remains of reindeer. You can see one of the mandibles illustrated in the bottom right. And of course, the big question for me was if these things had, I mean, you know, the upper entrance didn't exist at this time. It hadn't been made. So how had this material got into the cave? And it was quite clear there had to have been another entrance. As we found, there was beautiful remains of hyena, huge spotted hyena. This is the back part of a jaw in the top left, shown next to the largest spotted hyena that I have in my comparative collection. Lots of remains of young reindeer, which seem to have been the prey of the hyena. On the top right, you can see this mandible of a young reindeer, and hopefully you can see where the arrows are. These are the milk teeth with the adult teeth waiting to push up underneath. So this animal is about 4 to 5 months old, and we're now starting to think whether this is giving us evidence of reindeer migration, that perhaps, as animals do today, they have their calves further to the north and then move further to the south over winter. So they could be calving in the Midlands, for example, in the Peak District, and then making their way to the southwest, which would be consistent with the age of these animals. Bottom right, we've got a beautiful skull cap of a baby reindeer. So you can see the forehead and the little antler bases. And extraordinary, our first evidence of humans in the cave. It's a struck flake. It's white patinated. Flint isn't a local material. You have to go about 10, 12 miles to the east in the direction of Frome to be able to pick up flint, but obviously it would have been a very prized resource. And this flint flake has got all the hallmarks of human manufacture. It's got a platform, it's got a bulb of percussion, so the shock waves traveling away from the point where it was struck, and these ripples coming away. And there's further removals on the other side of the piece. Probably this was from an individual who came along, hopefully while the hyenas weren't home. This would not have been an attractive place for people to occupy with large carnivores around, but someone did come by at some point, perhaps did some napping outside the cave, and this is just one of the things that may have pinged off over their shoulder and landed in the cave. And as we began to work towards the front of the cave, we've still got, as you can see, our archive section. We began to pick up something that looked a bit like a sort of alcove. You can see the light shining through the upper entrance above. Now, outside, of course, all of this was covered in a talus slope of pretty coarse breccia. And of course, the temptation was to go from the cave and to just burrow out. But of course, we couldn't do that safely. We had to come from the outside and to take this down systematically. But gradually, we began to expose this sort of lip that was appearing, and maybe it was a connection to the cave. And in fact, actually, as we went down, a hole appeared. One of my colleagues climbed into the upper entrance, went down to the bottom and poked his hand up through like a zombie so that we could see that there was a connection. And there, that lower entrance is starting to emerge. So this is the entrance. Before the upper entrance was created, this is the entrance from about 40,000 years ago through which the hyenas entered and they brought their prey. Some fabulous remains of woolly rhino have come up. So some beautiful associated milk teeth of a baby woolly rhino. By analogy with white rhino tooth eruption, I think this animal was about 2 years old when it was killed. Many of the large mammals, mammoths, woolly rhinos, they would have been unassailable as adults. But we know that the babies, if they could be separated from their parents, they were literally fair game for these large predators. So the other half, I was always hopeful that we would find the other half of the tooth row. The only thing I've found is the horribly digested part of one of those teeth, which has obviously passed through the hyena. And on the right-hand side, this was a lovely find made quite early on in our season this summer. So this is one of my former students. She has a proper job as a tax accountant now, but she comes back every year and digs with us. And it's a beautiful piece of sub-adult. It's not juvenile. It's not the same individual as the one on the left, but a sub-adult woolly rhino humerus. And it's been completely gnawed at the top end where the hyenas have got into it and have been gouging it out to extract the bone marrow. So during this period when the hyenas are active, this is the middle part of the last ice age. It's an environment that is an extinct ecosystem that's often referred to as the mammoth steppe. Unlike tundra environments today, which are very poor environments, they can't support large herbivores in any great numbers. This was a very productive biome, and it's quite dry, and that dryness is exacerbated by the grazing activity of the animals themselves, but low precipitation and low snowfall, and that suits things like woolly rhinos very well because they're not well adapted to high snow cover. By analogy with, well, sort of extrapolation rather, from sites that are out in Siberia where there are abundant remains covering this time period, the biomass of the herbivores has been calculated at about 10.5 tons per kilometre squared. Now that is not far off what we see in East African savannas today, which have the highest herbivore biomass. And it should really bring home the fact that we have this enormous open environment. The herbivores are grazing, they're browsing off all the trees, so it's relatively treeless, but there are just huge numbers of mammoth, of woolly rhino, bison, reindeer, wild horse, occasional giant deer, and all the predators that are following along after them. We can still see a tiny, tiny remnant of what this might have been like up on Wrangel Island in the north of Siberia today. And that's because this is a landscape that is heavily modified by reindeer grazing. And in fact, even in July, summer temperatures are only just above freezing, and yet there is impressive photosynthesis of the grass, and that's because we have this high animal nitrogen input by the dung of these animals. It's very dry. We can see species coming into the cave that today are found well to the east. So things like European ground squirrel today have a distribution in the dry steppic areas of Central and Eastern Europe. And we know from the very presence of woolly rhino that this period predates 35,000 years ago. So we're about 40 to 45,000. And that's because our woolly rhinos go extinct in Britain at about 35,000. You can see here a range of radiocarbon dates plotted against the Greenland ice core. And woolly rhinos are particularly abundant during sort of, 50 to 40,000, but then they start to disappear from Britain. And in fact, the youngest ones that are found are just ahead of 35,000 years, and those come from a site up in Glasgow. Elsewhere, the range contracts at about 20,000 years ago during the period of the last glacial maximum. But it's also a time of incredible turnover in small mammals. And we've only just realized this because of the power of ancient DNA. So this is a study that was done a few years ago now by Selina Brace and colleagues. And it's looking at the DNA from collared lemmings from a site in the UK and a couple of sites in Belgium. And here you can see the radiocarbon dates for different genetic clades. So different genetic groupings plotted out against the Greenland ice core, so going from oldest up towards the Holocene. Now, if you were just to find the remains of collared lemming in the site, you would think, oh, this species is pretty much present all the way through. But what the genetics is telling us, or are telling us, is that these are different genetic groups. Every time we go into one of these brief, warm, abrupt warm events, an interstadial, the lemmings go locally extinct in Britain. And when we go into a cold stadial, one of these brief cold periods, a new wave of lemmings comes into Northwest Europe. So we're actually starting to see population level turnover now, which is incredibly exciting in terms of trying to map that onto what we see with what we see with abrupt climate change. So starting from the point where we began with the cave, the upper part of the cave records the period from about 14,500, the late glacial interstadial, the climatic deterioration of the younger Dryas, and then up to about 10,000 years ago when the cave is infilled. However, we can now take that record back to about 45,000 years. So those are the oldest radiocarbon dates that I have for the material. And this is incredibly exciting because this site is the best archive of its kind anywhere in Britain, and one of the most important in Northwest Europe for understanding these very abrupt changes and the impact that they have on the mammals. I'm not claiming that this is a continuous record, because of course, you know, that's not the case. There will be gaps in this record, but nevertheless, this is giving us an unparalleled and rich insight into this extraordinary period. It's been a great place to do work, a fantastic place to take students. You can see from the middle photo, and in fact you saw it already in the fly through the cave, that we had to take the witness section out. Disappointing, but the deposits were not kind to us. Behind our wooden boarding, we had a sandwich of deposits. The middle Devensian, the last cold stage deposits, hung together very well. They were well matrix supported. The late glacial deposits hung together very well. But those 2 meters of last glacial maximum, about 25,000 years ago, that were really coarse and had no matrix, we could hear them slumping away inside the box. So the worry was eventually the top material would be compromised and would slump down, and there was no justification for leaving it. And because we had dug in such detail in the north side of the cave, we came to an arrangement with the National Trust and Natural England that we would take out that remaining quite thin part, actually, of sediment. So now we are back onto the bare rock, and you can see here the 2 entrances. We are still going down. So this summer, you know, we still found a lot of material. I don't know where the floor of the cave is. Obviously, when we find the floor of the cave, that will be the end of the story, because we will have completely removed the cave infill at that point. And I just want to close with a few words about why this is important. I mean, you know, I think the story of these Ice Age mammals is fascinating in its own right. The reconstruction of these past environments, painting the backdrop to the extinction of Neanderthals and the arrival of modern humans, the landscapes they inhabited, the species they interacted with. But nevertheless, there is an important applied side here, in that the more we know of these species from the past, the better we can conserve them today. So all of these important things that we would view as significant baseline information, so things like the natural range of species, and particularly the speed of change at which species can move. They can expand and contract their range. Habitats, prey-based competitors, non-analog communities as well. We need to stop seeing everything in such a rigid way. On the right, we've got a picture of a wildcat. So beautiful wildcat. It's our most endangered species today. We have remains from the early Holocene in Britain, showing that these animals were very happy in southern England, living in association with deciduous woodland, plenty of prey for them. Today, of course, we often erroneously refer to them as the Scottish wildcat, because that's the place where they have been able to survive. They're living a miserable existence in a marginal area up in a part of the country where they've not been completely persecuted to extinction. The best thing we should be doing is to try to reintroduce them in southern England. But of course, the problem down here is the number of domestic cats and disease transmission, crossbreeding as well. The integrity of the species would be threatened. But the knowledge of where they could and should survive gives us important information if we needed to make sort of drastic conservation decisions in future. We can also learn a lot about diet and ecological flexibility, so lots of ways that we're investigating that, and also about the establishment of native species. So at the bottom, I've got a little image of the common vole. Now, the common vole was illustrated in green right the way through when I was showing you the sequence of events. Because it's a species that is not found in southern England today. In fact, it's only found up in the Orkney Islands. And it was believed to have been imported by Neolithic farmers accidentally to the Orkneys. but it's not found in Britain today. As you can see from the map, actually the map in pink shows that pretty much all of Britain, apart from the Orkneys, is the territory of the short-tailed field vole. Further to the south in the blue, we have the area where the common vole is present, and in purple we see the area of overlap of sympatric distribution. But by doing some very detailed work on shape analysis of the teeth, because the teeth are very difficult to tell apart between these two species, we were able to identify certainly common vole in early Holocene deposits, and we double-checked that by DNA testing it as well. And this proves for the first time that actually the common vole is a genuine native species, and therefore it's deserving of greater protection as a native species. So of course these types of investigations can give us more information about our true natives and also about rewilding opportunities. So I hope that's given you some insight into what I've been up to since I last spoke to the group, and hopefully the potential of these types of sites for shedding light on biological responses to these very abrupt climate changes. This is the view looking out towards Glastonbury Tor from the top of the gorge. It's a wonderful place to work. I've been very privileged to have fantastic colleagues and students coming to help us over the years, and these lovely associations and individuals who have also sponsored us. We are entirely reliant on private funding, charitable donations. This is not grant funded, so every year I have to scrabble the money together, and I'm extremely grateful to these individuals for supporting us. So thank you very much, and I'm very happy to answer any questions.
Well, Danielle, thank you so much for that view. It really is showing us once again the vast amount of data and information that you have to process and develop as you go along. You're finding new ways of looking at all of this and new ways of processing the data. You say you don't know where the bottom of this is and how long this is going to go on, but I suppose it's there is no way of knowing at the moment, is there?
So people have asked whether we can do some kind of resistivity. The problem is, and maybe techniques have moved on, but when I explored this, probably 10 years ago now, I was told that there would be insufficient differentiation, that we had a limestone cave that was filled with broken up limestone, so it would be very difficult to actually determine where the floor was. It would certainly help us to know, I must say. So
yes, yes. Any questions or comments from anybody? John?
Sorry, me first?
Yeah, John Ratford, I saw you first anyway. Yes.
So you've got these species of small mammals that breed and breed, don't they? And am I understanding it right that the main reason why they change is to do with habitat and species competition? Is there anything about any particular groups of small mammals in their genetics that makes them more disposed to adapting quickly? Are some species sort of down a cul-de-sac that stops them adapting?
Interesting question. So I think for this period, out of the three options that I gave, it's either move or die. The climate changes are happening so abruptly that I think there is insufficient time to see adaptation. Certainly, I'm not seeing any particular trends with, for example, measuring teeth, for example, which is usually where you would expect to see this kind of thing. So the communities are shifting because they're trying to track their preferred environment, which is an alternative to evolving. The evolution that we do see, and in many mammalian lineages throughout the Quaternary, that is happening over longer periods, over thousands of years to tens of thousands of years.
Thanks.
Mark?
Yeah. What fraction of the complete mammal fauna do you think you've unearthed so far?
Do you mean in terms of what was actually in the cave, or do you mean, are there other species out there in the landscape that we probably haven't found yet?
Are there other species out there? I'm just wondering if you compare it to what we would see right now if there weren't any people around and we had a sort of natural environment.
So in terms of what we know about, let's say, the middle part of the last cold stage, I think we've probably got most of the species we're going to get. Yes, you know, we don't have things like mammoth, but I don't know how likely it is in a setting like that we're necessarily going to find bits of mammoth, unless a juvenile mammoth is killed by a hyena just up the slope and they bring it in. There are things like giant deer as well that we don't have. Some of the other bigger predators like lion, we know were around at this time. We don't have that either. So we know that there are some things that are missing, but we have them at other sites. So I think our knowledge overall of this period is quite good, but it's been based very much on isolated sites. This is the first time we've got a site that acts as a sort of long benchmark into which all of these other isolated finds can be slotted. So we actually understand that succession, because whilst we've always had, you know, for a long time now, we've had this sort of picture of the mammoth steppe fauna, you know, woolly rhino, woolly mammoth, horse, bison, and so on. Actually, you know, my big question is what's changing? These interstadial to stadial changes, are we actually going to pick that up? Is that going to start affecting, when's it going to start affecting the large mammals or indeed the small mammals? And we know that it is affecting the small mammals because we've seen that turnover with the DNA. So I think we will, I mean, you know, obviously it's great to, you know, to tick off as many species on our Ice Age bingo as we can. But I think we've got a good knowledge of what that fauna is. And my interest now is seeing how it responds to, you know, to these very abrupt changes. We've never had that opportunity to ask that question before.
Fascinating, yes. Other questions?
Oh, can I just show you a couple of things from Clacton Beach? So we've got material dredged from the North Sea, 10 miles offshore. So we've got lots of horse bones.
Oh, nice. Yeah.
And woolly rhino teeth. So we've got, yes, a lot of woolly rhino, mammoth, horse, different bovines, and Rachel Bino is looking at I think a dozen buckets of bones that we've collected over the last few years.
Yes,
She might be doing that this very moment.
At 9:15 of an evening, I hope so. That's a very good pastime for Rachel to do. No, I mean that's great, because of course, you know, part of our record will be, you know, we'll cover that period, you know, whenever, I mean, you know, I don't know how precisely you'll be able to date that material. It's probably a bit of a palimpsest, because it's, you know, it's from that sort of context. But of course, you know, that's what's going on the eastern side with all of Doggerland, and, you know, the obviously the species are coming in and out. They have to cross that area to be able to get into the southwest. So there will be continuity, and the mammoth steppe stretched all the way from the southwest pretty much all the way to China. So there's a, you know, a sort of continuous, you know, massive habitat for these animals to move around in. And one of the things I've become increasingly interested in is finding out about how far they've moved, actually. So, for example, with strontium analyses, we're just starting to do that kind of thing.
Oh, that's interesting.
It seems a bit of a dark art identifying mammoth species from just from the teeth. I know Adrian Lister's looked at one or two of ours, and I guess it's things like what habitat they're in at the time. Oh, would they adapt quickly enough with the number of ridges on their teeth? I guess possibly not, if things are changing very quickly.
Well, for the last cold stage, the only mammoth that is around is the woolly mammoth, Mammals primigenius. And, you know, the environment is pretty much the same from the start of that period through to the end. Obviously, if you're looking at a longer period, you know, if you're looking at 2 million years of mammoth evolution, then yes, we see very clearly the transition from Mammuthus romanus to Meridionalis to Trogontheri, and then changes within Trogontheri, and then Primigenius at the end. So you can see those changes over a longer period. But for the period that the woolly mammoths are around, you know, let's say, because they're not around in the early part of the last cold stage, we've got no record of them, you know, sort of about 80, 90,000 years ago. They come back at about 50,000 until they eventually disappear. And for that period, they're in a constant environment. It's, you know, that there are climatic oscillations, but you're not going to see changes in the teeth over that period.
I suppose the problem with the current climate change is, well, lots of problems that make it completely different from previous climate change events, in that it is incredibly rapid, for one, and secondly, it's inhabited by billions of humans. But is there anything at all that, looking at the records that you are developing from this one cave, is there anything at all that leads you to say, possibly this might be happening now because of what we've discovered in the past? Or is it so totally atypical?
I don't think the rapidity of change is necessarily atypical, because things have, I mean, I think it's almost impossible for us to understand that things could happen within the matter of a couple of human generations, that, you know, we could be living in a warm stage and our grandchildren could be living in an ice age, and it can change that quickly. And I think people find that very difficult. I mean, that's actually quite a good analog. And I think if there's a message that I can say, it's that expect change and disruption. So species, you know, were able to cope in the past by expanding their range. I mean, the bigger ones got into various difficulties, and probably the final nail in the coffin was human hunting. But in terms of even the smaller ones, if they've got room to maneuver, then they can, you know, they have been able to get out of difficulties. It will become difficult for the ones that are, you know, that are in their refugia now because they're cold adapted, because they have nowhere to go to. That is definitely going to be a problem. And currently my records from this particular cave don't go back far enough. If we get back into the last interglacial, then maybe I will be able to say something about that. But, you know, other things are able to move. The problem is that, of course, we've got high sea level at the moment, so there are large areas that they simply can't move in and out of, and also humans everywhere. So we may have to do sort of quite interventionist things, I think, in terms of translocating species to places that we know they survived in the past, because, you know, it replicates the kind of conditions that they need. So I think, you know, rapidity of change, you know, we are certainly seeing that. And, you know, the fact that species normally should be able to be quite resilient. I've got other work that we're doing, for example, looking at wolves in terms of ecological resilience, which is looking at sort of longer term changes, but also pairing that with geochemistry, so dietary reconstructions, microwear, which shows what the wolves were eating in their last few meals, and working with modern wolf biologists to, you know, give them this information, but also to receive back information about modern wolves, and actually looking at wolf scats as well. So actually the last meal as well. So there's an increasing amount of back and forth, you know, hopefully with ecologists, to try and show, you know, where there have been periods of resilience and what those adaptations have been in the past. The more information we can feed into this, the better.
Yes, I guess and hope that interdisciplinary collaboration is becoming more and more prevalent, and it's an extremely good thing. Yes, excellent. Thank you.
One more question. Have you found much evidence of reptiles in in what you've dug up? Snakes, lizards, and
So I didn't have time to talk about reptiles, amphibians, fish, or mollusks. But yes, there is, it's pretty constant and unchanging. The last cold stage, you don't get very exciting reptiles and amphibians. We have frog, common toad, the occasional lizard, bit of grass snake, bit of adder. And that's what we've got. Yeah, it's not like, you know, fabulous sites like Cudmore Grove, for example, where you've got, you know, an interglacial and exotic herb species and things like that. So, so they are present, presumably being brought in either by small carnivores or birds of prey. But of course, you know, they will also find their way naturally into caves as well, because they just seek shelter in the caves too. So, yes, they are present.
Thank you.
thank you.
Well, if there are no further questions or comments, I'd like to thank Rachel for coming back to talk to us. Danielle, sorry, for coming again to talk to us again, this time by Zoom. And I thought that was an absolutely fascinating look at the kind of work you're doing, the kind of collaboration, and the amount of work that is being put into this. And we wish you every bit of luck for the future in financing this to continue. And I think I said the same to you last time we spoke, because it is so precious, this research. And I would say it's getting on to be vital for our existence. The more we find out, the more we collaborate, the more chance there is for humans to continue. So no pressure there.
Thank you so much, Ian. I mean, it's lovely to have the support, and thank you to everyone for listening.
Thank you so much, and we hope we see you again before too many years is up.
I hope so. Thanks, everyone.
Bye-bye.
Bye.
Thank you. Bye.
That was great.
Yeah, that was fascinating, wasn't it? That was
tremendous.
yeah.
Another look at the amount of research that is being done, the amount that they have to consider when they're doing their research, which I think we found from our last few talks about the North Sea and about offshore archaeology and so on, that it is painstaking and voluminous research. And thank goodness there are a few people around still to ensure this and coming up through the ranks to do it. But I always get the feeling it's just not enough people doing this kind of work. So
yes, I know in biology and ecology, there's fewer taxonomists now, fewer people to identify things. I don't know if it's the same in archaeology.
I wonder, yes, interesting, isn't it?
Why is that, John? Why are they
maybe less fashionable? I know at Essex University, students would rather watch dolphins than learn how to identify species, things like lacewings down to species level. But then again, it depends how things are pitched. So they loved going on tropical field courses and learning all the fish on the coral reefs. They seem to be very good at it.
Well,
just make it more exotic.
This was one of the problems with geology during this time period, was that David Bridgen's students were pretty keen on going to Portugal, but didn't really want to count pebbles on the hill at Langdon Heights in the middle of Essex for some reason. It would be very useful to know more about that gravel and its derivation. So yeah, yes, it's fashion and attraction to particular courses. Yeah.
Courses are very competitive now, aren't they?
Yes, for the time being, anyway. Yes. Yeah. Well, that was tremendous.
Yeah, really good, wasn't it? Yes.
Yeah, well, that's well done, Ginny, wherever you are, for arranging that one.
Another good one, yes.
Yeah.
It's lovely because Zoom's given that opportunity, hasn't it? Because Danielle's over on the west of London, and to come across to
Yes,
speak to us in person is really not.
it will be pretty
possible.
horrible. Yeah.
I mean, she has done in the past, but it's
Yeah.
not a journey that would. It's very attractive with her commitments elsewhere as well.
Yes, that's the main thing. So we're very happy to carry on with these Zoom chats as well as at Stanway and Shenfield. And I see no reason why we can't carry on doing this. So with your support, that's wonderful. Thank you very much, everybody.